So what I thought we would do is go ahead and draw by hand the first Bessey shuffle diagram on the top left, up over here. We'll do just one of these by hand, just so you can see how it's constructed. Okay, so for this shuffle, the left-right shuffle, on which we stack the left pile on top of the right, leads to the following permutation. So 1 gets sent to 7. Okay, so what you do here is you start at 1, 1's right there, and you draw an arrow for 1 to 7. That's all you do. So I'll just draw an arrow from 1 to 7. And the direction is as follows. We're going from 1 to 7. Okay, so 1 to 7, 7 to 4. Okay, so 7 goes to 4. And in just a moment, I'll give you some additional ways of interpreting this 7 goes to 4. What does that really mean? Okay, so we'll give you some practical ways to make sense of that statement. Now, going back to our cycle notation, 4 wraps around and gets sent to 1. So that means we just draw a line straight up. And it would go with an arrow pointing upward because it's 4 goes to 1. Okay? So now we have to look at this second term in our permutation. So 2, 5, 8. Okay, so 2 gets sent to 5. So I'll draw a line, a directed line, an arrow, from 2 to 5. Just like that. And then 5 goes to 8. Okay, so it just goes straight up from 5 to 8. Just like this. Okay, and then 8 wraps around and goes to 2. So 8 goes to 2. Okay, so we draw a line from 8 to 2 with an arrow pointing towards 2. Okay, and then something else interesting happens because 3 is not present, and we already know that it's a fixed point. What that means then is you can just draw it with no markings at all as far as an arrow, which is what's done on the computer drawn version up there. You can also do this, which is just fine, where it's indicating that 3 is sent to 3. 6 is sent to 6. So they don't move anywhere. They're fixed points. And then let's take a look at what's happening with set A. Remember, the set A consists of the values 1, 4, 6, 7. Well, what's found in positions 1, 4, 6, 7 either stay where they are in the case of 6, or they get assigned to one of the other values in that set. 1, 4, 6, 7. So we would say that A gets sent to A. Well, once we know that, then we also know that A complement, which are the red vertices there, red points, so 2, 5, 8, and 3, those get sent somewhere to themselves. Either they're fixed, as in the case of 3, or they just get moved around, permuted among themselves, at 2, 5, 8. So in this case, we would say that this shuffle preserves Bessey sequences of order 8. Okay, now in a minute we're going to do another shuffle where it inverts it. It sends A to A complement and A complement to A. Now that will pose no difficulties for us moving forward. That is perfectly acceptable for that to happen. It will not undermine anything we hope to do. So I thought I would give you kind of a metaphor or narrative to make sense of the colored dots on our diagram and the arrows pointing in certain directions. So what I want you to do is picture, if you've seen Monty Python's spoof involving I think it's maybe a 100-meter dash, where you have these ancient figures, Archimedes and Karl Marx and other philosophers running. seeing who can run the fastest. Okay, so it's just a silly little Monty Python spoof. Okay, so these are their starting positions. So this guy here, William the First, starts in the first position. Edward Elder in the second, and then we have third, fourth, fifth, sixth, and then all the way to Ethelred in the 8th position. Okay, so what we want to do is we're going to have them run this 100-meter dash, and then we'll see how each of them did at the end. Now the way that we'll get the new ordering for these runners is we'll just perform this shuffle that we've just done. The LR with left stacked on right. Okay, so I'll do left, right, left, right, left, right, left, right, stack left on right. Okay, that's the shuffle we've been doing. Okay, now we know what order is going to come out because we've seen it already, right? So we're going to get, of course, 7 will be first, then 5, 3, ace or 1, 8, 6, 4, and then a 2. Okay, so that agrees with what we did earlier. Now the way to think about these is when we're looking at the diagram here that we've just drawn, is think about it in this way. First, so the race has been completed. Okay, they've run, and this is the new, this is the first person to cross the finish line, second, third, all the way up to the last person, the loser over here, last person to cross the finish line. Okay, so what does this mean? This means that first place goes to the individual who was originally in 7th place, right? Because we had them ace through 8 originally. 7th place, over here, this is 7th place, goes to whoever was originally in the 4th position. And that's what we see here. 4th place, which is over here, goes to the individual who was originally in position 1. And that is the person, William I, was originally in position 1. Okay? So this is a way of interpreting really what's going on. So we say first place goes to whoever started in the 7th position. So the arrow going from 1 to 7 is best interpreted in that sort of way. So first place, so the new first position, first place goes to whoever started in the 7th position. And second place goes to whoever started in the 5th position. So is that true? Second place goes to the person who originally started in the 5th position. That's true. We see it right here. The second place winner is now the 5 of hearts. And that 5 of hearts started in the 5th position. Okay? So you can think of these as assigning a new placement order to the cards after the shuffle has been completed. And we can read it from here. So first place goes to 7, the card that was in position 7. 7th place goes to the card that was in position 4. 4th place goes to the card that was in position 1. Second place goes to the card that was originally in position 5. 5th place, right here, goes to the person who was originally in position 8. And 8th place over here goes to the person who was originally in the 2nd position. Okay, so that's a way to interpret these permutations written in cycle notation or as a shuffle diagram, as depicted here. So I'm hoping that explains how it is I got this diagram here on the left for the permutation that results from performing this particular shuffle. And as some specialized vocabulary, we say that 2, 5, 8 are in the same orbit. So that's a technical word from group theory. So one orbit is the set consisting of 2, 5, 8. Okay, oops, sorry about that. So that's one orbit. I'll say orbits. Another orbit is one consisting of just 3 because it doesn't go anywhere. And then two other orbits, I'll go ahead and just do them in black because we have them color-coded in black, will be 1, 7, 4. So it's like they just cycle around. They just trade places sequentially there. So 1, 4, 7. I've just listed them in order, which doesn't matter when you're writing set notation. And then the remaining orbit is the one over here for 6. 6 is in its own little orbit, since this shuffle leaves 6 alone. And the important thing to understand regarding Bessey sequences is that all of the red values after the shuffle will stay within positions marked by the red values, and the same thing for the black values here. After the shuffle, they'll stay in positions that are marked black, namely 1, 4, 6, 7.